Welcome to this session of Loose Talk about physics. Today I will use some time to discuss numbers, different kind of number sets and their quality and their physical significance. As some of you may know who has studied nature courses, there's a difference between mathematics, theoretical and applied, and physics, of course. And this is pretty important because sometimes something that can be described by mathematics doesn't really apply to anything other than theoretical at best. So here we have the natural numbers and the whole numbers. The natural numbers are this, and the whole numbers are this. And actually some of this, what I'm thinking about to discuss with you has an historical beginning. A very important person in this respect is Georg Cantor. He was a mathematician who described qualities of different kind of infinities. For example, this row of natural numbers from 0, 1, 2, 3, 4, 5, 6 goes on for eternity. But the amazing thing about this is that this number set, which is whole numbers, I mean all whole numbers, even the negative ones. This one, where it's possible to see that this infinity goes on forever, 6, 7, 8 and 3, 4. This infinity, the set infinity, is the double, it has a double size than these natural numbers here, because here it starts a set that contains all whole numbers except the negative ones is less in size than the one who has negative numbers as well. It's possible to see. Mathematics and infinities. How are they interesting? Well, some of us has discovered that we are living in the space age, and the new frontier is out there in space. But how do we get there? There must be some physics that we have to discover to create things we need, maybe for interstellar travel, like exotic things as antimatter, negative energy, and so on. But it's like and for describing those these different infinities is, for example, for whole numbers, go 0, 1, 2, 3, 4, and if you have a Q here with dividends and such, there are more points in this one, just as there are more points in set here than n, the more points. So there, it's the resolution of this these numbers are higher here, and maybe and what I'm trying to make you, what I'm trying to what is most important here is this Planck length. It's an incredibly short length. It's 1.6 times 10 to the minus 35 meter, and this Planck length is supposed to be it's a tool for discussing particles, subatomic particles, quarks, and what have you, the qualities of them. It's supposed to be a length that's which resolution further down, like minus 35, minus 36, minus 37, thinks that it doesn't make sense, that it resonates with nothing in the physical world. For example, if this suddenly was to be 75 instead of 35, it wouldn't be any meaning to give a higher resolution to a length like the Planck length. So I was wondering if, like, physics around us, physics in the sun's in the vicinity of Earth's orbit, space near Earth, space near the sun, qualities like, let's say, for example, the Planck length. Is it reasonable that this Planck length changes in accordance with distance from a gravity well, from the sun's gravity well, from the Earth's gravity well, and things like that? The sun's gravity well is actually pretty large, because the sun is a big mass. The magnetosphere of the sun is far beyond the orbit of Pluto. So does physics change through interstellar space, or through a travel through the galaxy? And does this mean anything for particles that has this length? And if it does that mean that we can stimulate anything, stimulate space in a way that predicts a new physics? So I was thinking like this. I tried to draw a wormhole here, so that this is a shortcut through space. That's what the wormhole is, and that's why wormholes are interesting. Instead of going all the way around, you can take the shortcut. And that's supposed to be, it's the same thing here with this mountain. The car driving through the mountain, the tunnel, it's taking the shortcut instead of a long way. So if we learn how to drill holes in space like we drill holes in mountains, we could maybe come to a nearby star by using a shortcut, by drilling holes in space, so to say. So we can get there. It's just as far-fetched as the thought that for 200-300 years ago that we are able to drill holes for cars to drive in through mountains. Maybe we will discover how to create negative energy, antimatter, things that are needed to create shortcuts in space. Maybe we'll be able to do that 200 years from now. That would be interesting. So